Hello everyone. So today we will start to talk about chapter 6, Deflection of Beams. Because of copyright reasons, I cannot include music video in this beginning of my video. But if you have been used to start a class with the music, I can give you this. So today we will have Dua Lipa's New Rules, okay, to start our class. I think you can easily find this music from YouTube or Amazon Music. Right, so I feature this song because we will talk about some new rules today that you have not learned before in previous chapters. We use these new rules and new methods to solve the deflection of beams. Today is supposed to be a lecture 17, so we will talk about the integration method and superposition methods for simple beams to solve the deflection problems. So we will introduce the deflection of beam, derive basic deflection equations by integration, and calculate deflection at a random point by superposition method. So as a review, let's look at the previous equations we have learned. So far we have learned several different types of structural elements, or they are axially loaded elements, torsional element, and beam. For each one of them, we have learned how to calculate the stress and the deformation. For axially loaded element, the stress is just simply calculated as sigma equals F over A. Right? That is the loading over area. And for the deflection, that is how its length will change. Right? Will it become longer or shorter? Right? That is delta equals FL over EA. And for torsional element, we do not care about its normal stress. We only calculate the shear stress. Right? That is the tau equals TC over J. And its deformation is not become longer or shorter. It's kind of angle of a twist. Right? That is phi equals TL over GJ. And we have been talking about, like, you can compare these two equations. Well, you can find the loading, length, modulus, and section properties, that is A and here is J. Right? So these two equations are very similar. When it comes to beam, we have learned the equation in chapter 5, that is how to calculate bending stress. Well, this is kind of normal stress. So this theta equals M by C over I. Right? This is the central equation we have been using in chapter 5. We left the equation in chapter 5, that is how to calculate the deformation of beam. Right? I didn't give a solution, an answer in chapter 5 because this is a hard question to answer. But when we talk about deformation of beam, it had at least two components. One is called deflection, and we can use delta to denote its deflection, and another is called angle of a twist. It's a slope, or theta. Let's just simply look at a simply supported beam. So when we add the load here, it will be bended in this way, right? So if you look at a random point, let's see at this point. So this point will move from the original position to here. So this distance is called delta. Well, we call this deflection at this random point. So if you look at this point again, after deflection, you will have an angle between the tangent direction and the original direction. Here is theta, and we call this theta slope. Right, so these are the two components of the deformation of a loaded beam. I can tell you that actually you cannot find an easy equation, a unified equation to solve these two components. Which equation we'll use, or what method we'll use, will depend on the distribution of load on this beam. So sometimes it can be concentrated load, sometimes it can be distributed load with a constant W, or even some randomly distributed load with the W0 as the maximum value. Right? So it depends on the distribution of the loading applied to this beam. So in the first section, section 6.1, we will talk about an integration method. So here in the first slide, we show the deflection of a beam. Why this is a random, simply supported beam. You can see the loading distribution is very complicated. You have a distributed load W, you have a concentrated load P, and you have a concentrated bending moment at the right end. So starting from the loading, at a random point, you will have, as I just mentioned, you will have a delta, and that is the deflection, and you have a theta, that is the slope, and the theta equals the d delta x over dx. Okay. Sometimes if you look at some textbook, you will see they use V. They use V to denote deflection, and here we are using delta. Well, you should keep in mind that these two things are the same in this chapter. So we will use V sometimes and we use delta sometimes, and they are interchangeable in this chapter. Okay, just keep this in mind. Okay, so if we start from the loading distribution and we do a one integration, so you will get the shear distribution, Vx. Right, this is actually the practice of how do we determine the V's and how do we draw the V diagram. And starting from V distribution, how can we determine the bending diagram? Just please recall your memory about this method. How do we draw the bending moment diagram based on a V diagram? Actually, we calculated the areas, right? The areas in this V diagram. Then we consider the areas to draw the bending moment diagram. So what is the nature of calculation of area? It's a kind of integration, right? So that is to say, if you do another integration to the V diagram, to the V distribution, you will get the distribution of bending moment. So this is, you do integration from the loading, you will get V. You do another integration from V, so you will get M distribution. And I can tell you that if you do another integration, you will get the distribution of slope, the theta x. Strictly speaking, that should be the EI times theta x. So if you do the fourth integration, you will get the deflection distribution function, that is the delta x. So here should be theta. Okay. So in the opposite direction, if you already know the distribution of the deflection, that is the delta x. Normally we call this elastic curve. If you already know the elastic curve, that is this red curve, and you can do a first derivative. This is the first derivative, you will get the slope. The second derivative, you will get the bending moment. The third derivative, you will get the shear force. And the fourth derivative, you will get the loading. Okay, here in this slide we give more details to demonstrate this method, the integration method. And this is the easy example, simply supported beam with a concentrated load P. So you can easily determine the reaction forces, that is half P on the left-hand side and half P on the left-hand side point C. I believe everyone knows how to draw the V diagram. Right? This you get a 2 constant P over 2. So if we want to determine the moment diagram from the V diagram, what's our practice? Okay, we calculate A1 and A2, right? And again, the calculation of the areas is actually kind of integration. Right, the A1, you can easily calculate that the A1 equals P over 2 by L over 2, you get PL over 4. And here the A2 is just a negative PL over 4. Right. Then starting from the shear diagram, if you want to draw the moment diagram, right, to start at 0, since you started from a pin support, right, that's 0, and you add the PL over 4, and then you get the number, the value at the point B, right, is PL over 4. Then you use a straight line to connect these 2 points. Then you reduce the same area to point C. So you got the moment diagram. But then, as I mentioned, if you do another integration, you will get the slope. But before that, let me ask you where you have 0 slope. It's after deflection, after deformation of this beam, where you have 0 slope. Okay, here is a elastic curve after deflection, after deformation. Right? So do you have 0 slope at the supports at point A? Of course not. Well, here you will have slope theta. It's not 0. Right? How about here at the right hand side at point C? This is tangent direction, original direction. You have theta here. It's not 0. So where you have 0 slope? Well, the answer is here, right? At point B, you will have 0 slope, and you have maximum slope at point A and point C, the 2 supports, right? So after you do integration, you will get a second order distribution curve, as shown here, right? Then from here, from the slope to deflection, we need to do another integration. But before that, where you have 0 deflection? Where you have 0 deflection? Of course, you will have 0 deflection at point A and point C. Right? Those are the 2 supports, right? Pin support and roller support, not allowing the beam element to have any vertical deflection. At these 2 points, you have 0 deflection. Where you have the maximum deflection? Obviously, that is point B. Right? So here you will have a third order curve, as shown here, with 0 value at these 2 supports, and the maximum value at the mid span, at the point where you added the load P. Well, those are called the boundary conditions, like where you have 0 slope, maximum slope, where you have 0 deflection or maximum deflection. Those are boundary conditions that we need to use to solve the differential equations, then to feed our integration methods. So then I will solve a couple of examples to illustrate how do we use the integration method to solve the deflections and slope of a loaded beam element.